At first glance, the idea that the universe is expanding might seem like a straightforward concept. After all, we've known since the early 20th century that the universe has been growing ever since the Big Bang. We observe galaxies receding from us, with their light stretched by the expansion of space, a phenomenon known as redshift. The evidence for this expansion is irrefutable, yet it raises an even more mind-boggling question. What is the universe expanding into? The concept of an expanding universe was first proposed by the Belgian astronomer Georges Lemaitre in the 1920s, building on earlier ideas from Albert Einstein's theory of general relativity. Lemaitre suggested that the universe originated from a single point, a primeval atom that exploded in a cataclysmic event, what we now call the Big Bang. This idea was groundbreaking, but it wasn't until 1929 when American astronomer Edwin Hubble discovered that galaxies were moving away from us that the concept of an expanding universe began to gain acceptance. Hubble observed that the farther a galaxy is from Earth, the faster it is moving away. This observation, now known as Hubble's law, confirmed that the universe was indeed expanding and that space itself was stretching between galaxies. The idea that space itself is expanding is key to understanding the nature of the universe. This isn't like an explosion in which matter is being hurled out into a pre-existing void. Instead, the fabric of space-time itself is stretching, carrying galaxies along with it. In this model, galaxies are not moving through space. Rather, the space between them is expanding. This concept can be difficult to wrap your mind around because it challenges our everyday understanding of space as a fixed backdrop against which objects move. However, if the universe is expanding, we're left with a perplexing question. What is it expanding into? In our everyday experience, when things expand, they do so within an existing space. A balloon expands within the air, a room expands within the walls of a house, and the Earth's surface expands within the atmosphere. But the universe doesn't have an outside to expand into. It encompasses everything. So, if the universe is expanding, what is it stretching into? Is it expanding into nothing, or is there something else out there that we just can't see or comprehend? At first, the question might seem absurd. After all, we often think of nothing as being empty, an absolute void, devoid of anything. But when you think about the nature of the universe, this question becomes more profound. According to general relativity, space-time is a fabric that can be curved and distorted by mass and energy. If space itself is expanding, that means the very fabric of the universe is stretching and warping in ways that are difficult for us to intuitively grasp. The idea that the universe could be expanding into nothingness is also at odds with our understanding of physics. The laws of physics, as we know them, apply to observable space. But if there is no outside the universe, what does it mean to expand into nothing? Can something really expand into a void that has no existence at all? This question touches on the limits of our knowledge and understanding of space and time, and it challenges the very foundation of our conceptions of the cosmos. One possible way to approach this question is to think about the nature of the nothing that the universe might be expanding into. In modern cosmology, nothing is not simply a vacuum, a completely empty space with no particles or energy. Instead, we now understand that empty space is not truly empty. It is filled with what is known as quantum vacuum fluctuations, a kind of energy that arises from the uncertainty principle in quantum mechanics. This energy is not something we can observe directly, but it is a fundamental aspect of the universe, and it can have real effects on the behavior of particles and fields. In this sense, the nothing that the universe might be expanding into is not an absolute void, but a kind of quantum foam, a seething dynamic fabric of energy and potential. But even this concept of nothing raises more questions. If space itself is expanding, does that mean the quantum vacuum fluctuations are also stretching? How does this affect the behavior of the fabric of space-time? And if the universe is expanding into this kind of nothing, does that mean that space itself is being created out of nothingness? These are questions that scientists are still working to answer, but they highlight the fact that our understanding of the universe is still far from complete. Another way to think about the expansion of the universe is to consider the possibility that the universe is not expanding into a pre-existing space, but rather space itself is being created as part of the expansion. In this view, the universe is not expanding into an outside realm, but is rather creating new space as it grows. This idea is consistent with certain models of cosmology, such as the theory of eternal inflation, which suggests that the universe is constantly undergoing inflationary periods, creating new regions of space-time. According to this view, our observable universe is just one bubble in a much larger multiverse, and each bubble is constantly expanding, creating new space as it goes. The concept of the universe expanding into something or creating space itself brings us to a deeper philosophical question. What does it mean for something to exist outside the universe? In many ways, the idea of an outside to the universe is a meaningless concept. According to the laws of general relativity, the universe encompasses all of space-time. It is everything that exists. The notion of an outside suggests a boundary, but the universe has no boundary, no edge, and no center. It is a self-contained, all-encompassing entity. Therefore, the question of what the universe is expanding into may be fundamentally unanswerable within the framework of our current understanding of physics. Yet, the mystery of the universe's expansion remains one of the most intriguing puzzles in cosmology. While we may not have a definitive answer to the question of what the universe is expanding into, the very act of asking the question reveals the limits of our understanding. It challenges us to think beyond the confines of our everyday experience and grapple with the true nature of reality. As we continue to probe deeper into the fabric of space and time, new discoveries and new theories will emerge that may help us to better understand the true nature of the universe and its expansion. The mystery of the expanding universe also ties into one of the most profound questions in cosmology. What is the fate of the universe? If the universe is expanding, will it continue to do so forever? Or is there a point at which the expansion will slow down and eventually reverse, leading to a big crunch? Or is there some other unforeseen fate awaiting the universe, driven by the forces we are only beginning to understand? These questions are the subject of intense study and debate in the scientific community, and the answers may lie hidden in the deeper mysteries of space-time, dark energy, and the fundamental forces that govern the cosmos. The future of cosmic discovery holds the promise of answers to these questions and more. With advances in technology, such as the upcoming James Webb Space Telescope and new breakthroughs in the study of dark matter and dark energy, we may soon have a clearer picture of the universe's expansion and its ultimate fate. The quest to understand the nature of the universe, what it is expanding into, and how it all works, is a journey that is just beginning. And it is a journey that will continue to captivate the imagination of scientists and curious minds for generations to come. When we first gaze up at the night sky, it's easy to feel a sense of awe and wonder. The stars appear so distant, so small in comparison to our everyday world. But if we step back and think about the true scale of the cosmos, the size of galaxies, the distances between stars, and the enormity of space itself, it becomes apparent that the universe is beyond human comprehension. The universe is so vast, so unfathomably large, that it's nearly impossible to grasp its full scope. The question of the universe's expansion into nothing is compounded by the fact that we are dealing with a scale that stretches the limits of both our imagination and our understanding of space and time. The concept of scale in the universe is difficult to wrap our heads around because it is so far removed from the scales we encounter in our daily lives. When we talk about distances on Earth, they are measured in miles or kilometers, units that we are familiar with. But when we scale up to the size of the universe, those units no longer seem adequate. The vast distances between stars and galaxies are measured in light years. A unit of distance that represents the distance that light, the fastest thing in the universe, travels in 1 year approximately 6 trillion miles, about 9.5 trillion kilometers. The closest star to Earth, Proxima Centauri, is 4.24 light-years away. This means that the light we see coming from Proxima Centauri today left the star over 4 years ago. If you were to travel at the speed of light, it would take you over 4 years to reach that star. And that's just the closest star. The Milky Way, our home galaxy, is about 100,000 light-years in diameter, and it contains over 200 billion stars. In fact, our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. Each galaxy is made up of billions of stars, many of which are surrounded by their own planets, moons, and other cosmic bodies. To put it another way, if we were to try to travel to the farthest known galaxy, it would take millions of years, even at the speed of light. And yet, when we consider the sheer size of the universe, it's important to remember that we are limited by the observable universe. The observable universe refers to the portion of the cosmos that we can see and measure with our telescopes and other instruments. The observable universe is roughly 93 billion light-years in diameter, but this is only the part of the universe that we can detect. Beyond this, we don't know what lies in the vast expanse of space. It's possible that the universe extends far beyond what we can observe, and that's something we'll never be able to fully comprehend. The vast scale of the universe presents one of the greatest challenges in cosmology: understanding the true nature of space itself. Space is not empty. It's filled with galaxies, stars, planets, and other cosmic objects. But it's also filled with dark matter and dark energy, two mysterious components that make up most of the universe's mass and energy, yet remain invisible to us. Space is a dynamic entity, not a static backdrop. As the universe expands, the fabric of space-time itself stretches, carrying galaxies along with it. This stretching of space means that the distance between galaxies increases over time, and it's this expansion that we observe as the receding of galaxies. But the idea of space itself stretching is a concept that's difficult to visualize. When we think of an object expanding, we typically think of it expanding within a pre-existing space. For example, if you blow up a balloon, it expands into the surrounding air. But when we talk about the universe expanding, there is no surrounding space. There is no outside into which the universe is expanding. The universe encompasses all of space and time. So when we say that the universe is expanding, what does that mean? Is the universe simply expanding into nothing? The difficulty in understanding what the universe is expanding into stems from our limited conception of space. In everyday life, we think of space as something that is empty or vacant, but space in the universe is not an empty void. It is a dynamic, ever-changing entity that responds to the presence of matter and energy. The expansion of the universe is not like an object moving through space. It is space itself stretching, causing galaxies to move farther apart. This is a fundamentally different way of thinking about the nature of space. One way to understand this concept is to think of the universe as a balloon with galaxies marked on its surface. As the balloon inflates, the galaxies move farther apart from each other. In this analogy, the surface of the balloon represents the two-dimensional fabric of space, and as the balloon expands, the galaxies are carried along with the stretching of space. However, in the real universe, there is no surface of space. Space itself is three-dimensional, and its expansion is occurring in all directions, not just on a surface. The universe is expanding in every direction, and the fabric of space-time itself is stretching. This stretching of space is responsible for the phenomenon we observe as the expansion of the universe. The galaxies we see in the distance are moving away from us, but they are not actually moving through space. Instead, the space between us and those galaxies is expanding, causing the galaxies to recede from us. This expansion is not only occurring on large scales, such as between galaxies, but also on smaller scales, like between stars within galaxies. In fact, the expansion of the universe is happening on all scales, even though the gravitational forces between galaxies and stars are strong enough to keep them bound together. The expansion of space is still affecting their separation. As we look further into the universe, we see that galaxies farther away are moving away from us at greater speeds. This observation led to the realization that the expansion of the universe is accelerating. Initially, scientists thought that the expansion of the universe would slow down over time due to the gravitational pull of galaxies on one another. However, in 1998, two independent teams of astronomers discovered that the universe's expansion is actually speeding up, not slowing down. This shocking discovery, made through the observation of distant supernovae, revealed the existence of a mysterious force known as dark energy, which is driving the accelerated expansion of the universe. Dark energy is an enigmatic force that makes up about 70% of the universe's energy content, but it remains invisible and undetectable by current instruments. It appears to have a repulsive effect on space-time, causing the universe to expand faster and faster. The discovery of dark energy has profound implications for our understanding of the universe. It suggests that there is a force in the universe that we cannot see or measure directly, yet it has a significant impact on the large-scale structure and evolution of the cosmos. The expansion of the universe and the discovery of dark energy lead us to the question of the ultimate fate of the universe. Will the universe continue to expand forever, becoming increasingly empty and cold? Or will the expansion eventually slow down and reverse, leading to a big crunch where the universe collapses in on itself? The answer to this question depends on the nature of dark energy and the forces that govern the expansion of the universe. Some scientists speculate that dark energy could weaken over time, causing the universe's expansion to slow down and reverse, while others believe that dark energy will continue to accelerate the expansion indefinitely. The vastness of the universe, its continuous expansion, and the mysteries surrounding dark energy all point to a deeper truth about the cosmos. It is far stranger and more complex than we can imagine. Our current understanding of the universe is only a glimpse into the full reality of what lies beyond our comprehension. As we continue to study the expansion of the universe, the role of dark energy, and the nature of space itself, we will likely encounter more surprises that challenge our most basic assumptions about the nature of the cosmos. In the coming decades, advancements in space telescopes, particle physics, and cosmology will give us the tools to explore these mysteries further. Instruments like the James Webb Space Telescope, which will allow us to observe distant galaxies and the earliest moments of the universe, and the development of new theoretical models in quantum gravity, could provide new insights into the nature of the universe's expansion and its ultimate fate. As we look ahead, the question of what the universe is expanding into, and whether it is expanding into nothing, may become clearer. But for now, it remains one of the most profound and thought-provoking mysteries in science. The quest to understand the true nature of space, time, and the cosmos will continue to drive exploration and discovery, pushing the boundaries of human knowledge and unlocking the deepest secrets of the universe. Time and space, once thought to be the unchanging, solid foundations upon which everything else rests, are far more mysterious and complex than we could have ever imagined. For centuries, humans believed that time moved in a linear, consistent fashion and that space was a vast, empty container for objects to exist. The universe was a simple, predictable place, or so it seemed. But with the development of Einstein's theory of relativity and the rise of quantum mechanics, our understanding of time and space was revolutionized. These two fundamental concepts, which were once thought of as immutable, became dynamic, flexible, and deeply interconnected. The universe itself, as we know it, is no longer a static backdrop. It is a malleable, ever-changing entity shaped by the very forces that govern it. One of the most profound breakthroughs in modern physics was the realization that space and time are not separate and independent entities, as they were once thought to be, but are instead intertwined into a single unified fabric known as space-time. This discovery was made possible by Albert Einstein's theory of relativity, which transformed our understanding of how the universe works on both large and small scales. Before Einstein, the prevailing view of space and time was heavily influenced by Isaac Newton's ideas. Newton's laws of motion described a universe where objects moved through a fixed, unchanging space, and time flowed in a constant, uniform manner. In this Newtonian model, space was the stage on which events played out, and time was simply a ticking clock, ticking away at the same rate for everyone, everywhere. But Einstein shattered this concept with his theory of relativity, which revealed that space and time are not rigid, fixed entities. They are flexible and affected by mass, energy, and velocity. Einstein's first breakthrough, known as special relativity, showed that time and space are relative, meaning they depend on the observer's frame of reference. This idea came from the realization that the speed of light is constant. It travels at the same speed regardless of how fast the observer is moving. This leads to a phenomenon known as time dilation. When an object moves at a speed approaching the speed of light, time slows down for that object relative to a stationary observer. Similarly, space itself can stretch and contract depending on the speed of the object. The faster an object moves, the more space contracts in the direction of its motion. The idea that time can slow down or that space can shrink may sound counterintuitive, but it has been experimentally verified countless times. But it was Einstein's general theory of relativity that truly revolutionized our understanding of space and time. In 1915, Einstein extended his ideas to include gravity, describing it not as a force, as Newton had, but as a curvature of spacetime caused by mass and energy. According to general relativity, massive objects like stars and planets warp the fabric of spacetime, creating what we perceive as gravity. This warping of spacetime is what causes planets to orbit stars and what causes objects to fall toward the ground. The larger the mass of an object, the greater its distortion of spacetime. For example, the Earth creates a slight curvature in spacetime that keeps the Moon in orbit. The Sun creates an even greater curvature, keeping the planets in their respective orbits. What's more, this curvature of spacetime can affect the flow of time itself. The stronger the gravitational field, the slower time flows. This is known as gravitational time dilation. A clock placed near a massive object, such as a black hole, would tick more slowly than a clock farther away from the object. This effect has been confirmed experimentally by comparing clocks at different altitudes on Earth, where the stronger gravitational field at sea level causes time to pass more slowly than at higher altitudes. One of the most mind-bending implications of general relativity is the idea that space and time are not just passive, unchanging backgrounds. They are active participants in the events that unfold within the universe. Space and time are intertwined in a way that means they cannot be fully understood in isolation. The shape and structure of space-time are determined by the distribution of mass and energy, and in turn, the curvature of space-time influences how objects move and how time flows. This interdependence of space and time means that the very fabric of the universe is dynamic, constantly changing in response to the forces at work within it. The idea that space and time are not fixed and immutable was already revolutionary. But when combined with the discovery that the universe itself is expanding, it raised even more profound questions. The universe is not a static, unchanging place. It is evolving and stretching, and the very space in which everything exists is expanding over time. The expansion of the universe, first proposed by Edwin Hubble in the 1920s and confirmed through various observations, suggests that the distance between galaxies is increasing as space itself expands. This expansion is not like objects moving through space, but rather space itself stretching and carrying galaxies along with it. The expansion of the universe is one of the most fascinating aspects of cosmology. It was initially thought that the universe would eventually stop expanding and begin contracting under the influence of gravity, leading to a big crunch. However, the discovery of dark energy in the late 1990s revealed that the expansion of the universe is actually accelerating, not slowing down. Dark energy is a mysterious force that seems to be pushing galaxies apart, causing the expansion to speed up. Although we don't fully understand dark energy, its existence is one of the most significant revelations in modern physics, and it adds another layer of complexity to our understanding of time and space. To grasp the nature of this expansion, imagine the universe as a balloon with galaxies marked on its surface. As the balloon inflates, the galaxies move farther apart from each other. This analogy helps us visualize the idea that space itself is stretching, causing the distance between galaxies to increase. But the balloon analogy has its limits. It suggests that there is an outside into which the universe is expanding, which isn't the case. The universe has no edge, no outside. It is everything that exists. So when we say the universe is expanding, we are really talking about the stretching of space-time itself. But what does this expansion mean for the nature of time? If space itself is stretching, then what does that do to the flow of time? According to general relativity, the expansion of space-time does not affect the passage of time in a uniform way. The effects of expansion are most noticeable on cosmological scales, that is, when we look at the behavior of galaxies and other large structures in the universe. On smaller scales, such as within our solar system, space-time is not expanding significantly enough to have a noticeable effect on time. However, the expansion of the universe is still a key element in understanding the evolution of the cosmos. The idea that the universe is expanding, and that it has been doing so for billions of years, leads us to an even more profound question. What was the origin of this expansion? This question brings us to the concept of the Big Bang, the event that marks the beginning of the universe as we know it. According to the Big Bang theory, the universe began as a singularity, a point of infinite density and temperature, and began expanding rapidly about 13.8 billion years ago. This moment of expansion is often referred to as the birth of the universe, and it marks the starting point for everything we observe today. But what caused the Big Bang? What happened before it? And how does the expansion of the universe relate to the passage of time itself? These are some of the most fundamental and unanswered questions in cosmology. The answers lie at the heart of the study of the early universe in the period known as cosmic inflation, when the universe expanded exponentially in a fraction of a second. Understanding this period of rapid expansion could provide us with insights into the nature of time and space, and might even help us understand the origin of the universe itself. As we continue to study the nature of space-time, the expansion of the universe, and the mysterious forces like dark energy, we are confronted with the fact that our understanding of the cosmos is still in its infancy. The universe is far more strange, complex, and dynamic than we ever thought possible. The discovery of the expanding universe, the role of dark energy, and the stretching of space-time are just the beginning of a much deeper journey. The questions we ask today will lead to even more profound mysteries tomorrow, and the search for answers will continue to push the boundaries of human knowledge. One of the most perplexing and mysterious components of the universe is something we can't see. Yet, it makes up about 27% of the total mass and energy content of the cosmos. This unseen substance is called dark matter. It doesn't emit, absorb, or reflect light, making it completely invisible to the traditional methods of observation we use to study the universe. And yet, dark matter is one of the most important pieces of the puzzle in our understanding of the cosmos. Its existence has been inferred from its gravitational effects on visible matter, but what it actually is remains one of the greatest mysteries in modern physics. The concept of dark matter was first proposed in the early 20th century by astronomer Fritz Zwicky. Zwicky was studying the Coma galaxy cluster, a massive collection of galaxies bound together by gravity. He noticed something strange. The galaxies were moving much faster than expected, given the amount of visible mass in the cluster. According to Newtonian physics, the galaxies should have been moving slower, and the cluster should have been flying apart. Zwicky suggested that there must be some unseen matter, a dark matter, exerting gravitational pull and holding the cluster together. While Zwicky's proposal was groundbreaking, it took decades before dark matter began to gain wider acceptance. In the 1970s, astronomer Vera Rubin and her colleague W. Kent Ford made another key discovery that would further support the idea of dark matter. They studied the rotation curves of galaxies, which describe how the speed of stars changes as they move farther from the center of the galaxy. According to Newton's laws, stars at the outer edges of galaxies should be moving more slowly than those near the center. This is because the gravitational pull of the galaxy's visible mass, the stars, gas, and dust, should weaken the farther a star is from the center. However, Rubin and Ford found that the stars at the edges of galaxies were moving just as fast as those near the center, a surprising result that suggested there was more mass in the galaxy than could be seen. The most plausible explanation was that there was an unseen, invisible form of matter, dark matter, making up the majority of the galaxy's mass. Dark matter, it seems, doesn't interact with light or electromagnetic radiation in any way, which is why we cannot detect it through telescopes or other traditional methods. But while it's invisible, it does interact with gravity. In fact, dark matter's presence can be detected through its gravitational effects on visible matter. For instance, the rotation of galaxies, the motion of galaxy clusters, and even the bending of light, gravitational lensing, all suggest that dark matter exists. In addition, computer simulations of galaxy formation and structure rely on the presence of dark matter to explain how galaxies have formed and evolved. But what exactly is dark matter? While we don't yet know for certain, there are several leading theories. One of the most popular candidates for dark matter is a type of particle known as WIMPs, weakly interacting massive particles. These hypothetical particles would interact only through gravity and the weak nuclear force, which is why they are so difficult to detect. According to the WIMP hypothesis, dark matter particles would be far more massive than ordinary particles like electrons or protons. They would interact with normal matter only through gravitational and weak interactions, making them invisible to our current instruments. If WIMPs exist, they could potentially be detected through experiments designed to observe rare interactions between dark matter and normal matter. Another candidate for dark matter is the axion, a much lighter particle than WIMPs. Axions were first proposed in the 1970s to solve a problem in particle physics known as the strong CP problem, which had to do with the behavior of the strong nuclear force. While the axion is still purely theoretical, it has become a leading candidate in the search for dark matter due to its potential ability to interact with electromagnetic fields. Some experiments, such as those using superconducting materials or strong magnetic fields, are being designed to search for axions by detecting their interaction with light. However, just like WIMPs, axions have yet to be detected directly. Another, more radical possibility is that dark matter could be something fundamentally different from particles. Some physicists suggest that dark matter might be an entirely new form of physics, an unknown field or force that doesn't interact with matter in the way that electromagnetic or gravitational forces do. For example, theories like MOND, modified Newtonian dynamics, propose that dark matter might not be necessary at all and that the laws of gravity could behave differently on large scales. According to MOND, the anomalous motion of stars and galaxies could be explained by modifications to the law of gravity rather than the existence of invisible matter. However, while MOND has had some success in explaining certain phenomena, it has yet to explain all the observations that dark matter can account for, particularly on larger scales, such as galaxy clusters. While these theories are intriguing, the true nature of dark matter remains elusive. One of the biggest challenges in understanding dark matter is that it does not interact with light or any form of electromagnetic radiation. This makes it completely invisible to traditional telescopes, which rely on detecting light from distant objects. In fact, dark matter cannot be detected directly with any current technology. However, scientists have developed several indirect methods for studying dark matter, most notably through its gravitational effects. One of the most significant pieces of evidence for dark matter comes from the study of gravitational lensing. Gravitational lensing occurs when light from a distant object, such as a galaxy, is bent as it passes through the gravitational field of another object, such as a galaxy cluster. The amount of bending depends on the mass of the object causing the lensing. In cases where the mass of the lensing object is greater than what is visible, it suggests the presence of dark matter. In fact, gravitational lensing has been used to map the distribution of dark matter in galaxy clusters. These maps show that dark matter is not only present, but plays a critical role in the formation and behavior of galaxies. Another key observation that supports the existence of dark matter is the study of galaxy rotation curves. As mentioned earlier, when scientists studied the speeds of stars in the outer regions of galaxies, they found that they were moving much faster than expected. According to Newtonian physics, the stars on the edges of galaxies should be moving more slowly because there isn't enough visible mass to provide the gravitational pull necessary to keep them moving at high speeds. The fact that they are moving faster suggests that there is unseen mass, dark matter, that is exerting gravitational pull on the stars and keeping them in place. One of the most exciting developments in the search for dark matter has been the creation of dark matter detectors. These detectors are designed to capture the rare interactions between dark matter particles and ordinary matter. In particular, many experiments focus on WIMPs, as they are one of the leading candidates for dark matter. These detectors are typically located deep underground to shield them from cosmic rays and other sources of interference. As of now, however, no direct detection of dark matter particles has been made, and scientists are still waiting for a breakthrough. The search for dark matter continues to be one of the most active areas of research in particle physics and cosmology. The mystery of dark matter raises profound questions about the nature of the universe and the limits of human knowledge. We know that dark matter exists because of its gravitational effects on visible matter, but we don't know what it is or how it works. This invisible substance has a major influence on the structure and evolution of the cosmos, yet it remains beyond our ability to observe directly. It is a fundamental part of the universe, but it is also one of the most elusive components of the cosmos. Solving the mystery of dark matter is one of the greatest challenges in modern physics, and its discovery could lead to a deeper understanding of the forces that shape the universe. As we continue to study dark matter, we may eventually uncover the nature of this invisible force and unlock some of the deepest secrets of the universe. Whether dark matter is composed of particles like WIMPs or axions, or whether it represents a new form of physics entirely, its discovery will have profound implications for our understanding of the cosmos. Until then, dark matter remains an enigma, a mysterious force that continues to shape the universe in ways we can't yet fully comprehend. If dark matter is the invisible substance that holds galaxies and galaxy clusters together, dark energy is the mysterious force that drives the accelerated expansion of the universe. While dark matter is pervasive and helps explain the behavior of galaxies and cosmic structures, dark energy is perhaps even more enigmatic, as it seems to be responsible for the most surprising and profound discovery in modern cosmology. The fact that the expansion of the universe is not slowing down, as once expected, but is accelerating. This discovery, which fundamentally changed our understanding of the cosmos, was made in 1998 by two independent teams of astronomers studying distant supernovae. These teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, observed that the light from these supernovae was dimmer than expected, meaning the galaxies that hosted them were farther away than anticipated. Initially, scientists had thought that the universe's expansion would be slowing down because gravity should be pulling galaxies together, counteracting the force of the expansion. But the data showed that the expansion was actually speeding up. The astronomers' groundbreaking discovery that the universe's expansion is accelerating forced cosmologists to reconsider their models of the universe. To explain this unexpected behavior, scientists proposed the existence of dark energy, a form of energy that fills the fabric of space-time itself and exerts a repulsive force, pushing galaxies apart. This repulsive effect counteracts the attractive force of gravity, causing the expansion of the universe to accelerate. Dark energy, although it makes up about 68% of the total energy content of the universe, is still largely an unknown. It does not emit, absorb, or reflect light, making it undetectable by traditional observational methods. Unlike dark matter, which can be inferred through its gravitational effects, dark energy is detected primarily through its influence on the expansion rate of the universe. Yet, despite the fact that dark energy is responsible for the universe's accelerated expansion, we know very little about what it actually is. One of the challenges in understanding dark energy is that it behaves very differently from the matter and forces we are familiar with. Ordinary matter, such as the atoms that make up stars, planets, and galaxies, interacts with gravity, pulling objects together. Dark matter also exerts gravitational pull, helping to bind galaxies and galaxy clusters together. But dark energy behaves oppositely. It pushes things apart, causing the fabric of space-time to stretch. This means that while the matter and dark matter in the universe slow down the expansion, dark energy is the force driving it forward. The nature of dark energy is still one of the greatest mysteries in modern cosmology. There are several competing theories about its origin and how it works. The simplest explanation is that dark energy is a form of vacuum energy, a property of empty space itself. According to quantum mechanics, even empty space is not truly empty. It is filled with fluctuating energy, known as the quantum vacuum. This energy is thought to be constant throughout the universe, and it would exert a repulsive force on the expansion of the cosmos. This idea was originally proposed by Albert Einstein in 1917, when he introduced the cosmological constant into his equations of general relativity. Einstein added the cosmological constant to his equations to allow for a static universe, which was the prevailing view at the time. However, after it was discovered that the universe is expanding, Einstein abandoned the concept, calling it his biggest blunder. Yet, in the 1990s, after the discovery of the accelerated expansion, the cosmological constant made a comeback as a possible explanation for dark energy. The cosmological constant theory suggests that dark energy is a constant force that does not change over time. It has the same energy density throughout the universe and exerts a uniform repulsive force across all of space. This model fits with the observations that the universe's expansion has been accelerating consistently without any indication of slowing down. However, this theory also raises some questions. For one, it does not explain why dark energy exists in the first place or why it behaves in this particular way. Additionally, the observed value of the cosmological constant is far smaller than the value predicted by quantum mechanics. This discrepancy is known as the cosmological constant problem, and it remains one of the biggest unsolved puzzles in physics. Another theory suggests that dark energy is not a constant force, but a dynamic entity that changes over time. This theory posits that dark energy might evolve over the history of the universe, gradually becoming stronger as the universe expands. This idea, known as quintessence, suggests that dark energy is not a simple vacuum energy, but instead a more complex field that changes over time, similar to the way that matter and radiation behave. Quintessence models propose that dark energy could be linked to fields similar to those that govern the behavior of matter and radiation, and that its properties might evolve as the universe grows older. However, while quintessence offers a more flexible framework for understanding dark energy, it has not yet been confirmed by observations, and it remains speculative. Despite these theories, dark energy's true nature remains elusive. Some scientists have even proposed more radical ideas, such as the possibility that our understanding of gravity is incomplete. According to some alternative models, gravity may behave differently at large scales, which could explain the accelerated expansion of the universe without the need for dark energy. However, these models have not been widely accepted, and the overwhelming evidence for dark energy from multiple observational sources makes it the leading explanation for the accelerating universe. The impact of dark energy on the future of the universe is profound. If dark energy continues to accelerate the expansion of the universe indefinitely, it could lead to a future where galaxies move so far apart that they are no longer visible to each other. Stars will burn out, and the universe will become increasingly cold and dark. This scenario is known as the Big Freeze, and it represents one possible end to the cosmos. However, if the influence of dark energy weakens over time, the expansion could slow down, eventually reversing and causing the universe to collapse in on itself in a big crunch. This cyclical view of the universe suggests that it may go through endless cycles of expansion and contraction. While these possibilities are fascinating, the true fate of the universe depends on the nature of dark energy and how it behaves over the long term. One of the most exciting aspects of the study of dark energy is that it is an active area of research. Scientists are developing new instruments and methods to measure and study dark energy more precisely. The upcoming Euclid mission, launched by the European Space Agency, will study the geometry of the universe and the role of dark energy in shaping the cosmos. By mapping the distribution of galaxies and observing their motion, the Euclid mission aims to provide more detailed insights into how dark energy affects the expansion of the universe. In addition to space-based missions, ground-based observatories are also playing a crucial role in the study of dark energy. Large-scale surveys like the Dark Energy Survey, DES, and the Vera C. Rubin Observatory are designed to measure the distribution of galaxies and the large-scale structure of the universe. These surveys will help scientists map out the effects of dark energy on cosmic structures, and they may provide new insights into the nature of dark energy and its role in the evolution of the universe. The study of dark energy is still in its early stages, and much more research is needed to unlock its mysteries. But the discovery of dark energy has already had a profound impact on our understanding of the universe. It has opened up new avenues of exploration and forced us to reconsider our assumptions about the cosmos. Dark energy is not just a mysterious force. It is a key piece of the puzzle that could help us understand the future of the universe and the fundamental nature of reality itself. As we continue to explore the mysteries of dark energy, we will undoubtedly uncover new surprises that will challenge our current models of physics and cosmology. The search for answers to the dark energy enigma is one of the most exciting areas of research in modern science, and its discoveries will shape our understanding of the universe for generations to come. The concept of the multiverse, or multiple universes, is one of the most fascinating and controversial ideas in modern cosmology and theoretical physics. The idea that our universe might be just one of an infinite number of universes challenges everything we thought we knew about reality. If the multiverse theory is correct, then the universe we live in is only one bubble in a much larger, more complex cosmic structure, and our understanding of existence may be fundamentally flawed. This mind-boggling idea has sparked heated debates among physicists, cosmologists, and philosophers alike, as it raises profound questions about the nature of reality, the limits of scientific knowledge, and the very definition of existence. The term multiverse was coined in the 20th century, but the idea of multiple worlds or universes has roots that go back much further. Philosophers in ancient Greece, such as Democritus and Epicurus, proposed the idea that there could be other worlds beyond our own, though their ideas were based more on speculation than evidence. The modern multiverse theory, however, is grounded in cutting-edge physics and mathematics and arises naturally from certain aspects of quantum mechanics, string theory, and cosmology. One of the key pieces of the puzzle that leads to the multiverse theory is the discovery of cosmic inflation. In the 1980s, physicist Alan Guth proposed the idea of cosmic inflation to explain certain features of the universe that couldn't be accounted for by the Big Bang alone. According to the theory of inflation, in the first few moments after the Big Bang, the universe expanded exponentially, growing at a mind-boggling rate in a fraction of a second. This rapid expansion smoothed out the universe, creating the uniform, homogeneous structure that we observe today. However, the idea of inflation led to a new set of questions. If inflation could cause our universe to expand so rapidly, could other regions of space have experienced their own separate inflationary periods, creating entirely new universes? This is where the concept of the multiverse comes into play. In some models of inflationary cosmology, the process of inflation doesn't stop everywhere at once. Instead, inflation might continue in some regions of space, leading to the creation of pocket universes, separate self-contained universes with their own laws of physics and constants. These universes, according to this theory, would be completely disconnected from each other, and there would be no way for them to interact. Each universe would have its own distinct history and evolution, and the laws of physics could vary from one universe to another. The result is a vast multiverse of potentially infinite universes, each with its own unique properties. One of the most striking features of this version of the multiverse theory is that it suggests that the universe we observe is not special or unique. Instead, it is just one of many universes in a much larger cosmic landscape. In this view, our universe is the result of a random fluctuation in the early stages of inflation, and it could have turned out differently. The constants of nature, the strength of gravity, the mass of fundamental particles, and the behavior of forces could be completely different in other universes. In some universes, the conditions might not be suitable for life as we know it, while in others, life could be very different from anything we can imagine. This idea of a vast and varied multiverse raises profound philosophical questions. If there are infinite universes, does that mean that every possible outcome of every event happens somewhere in the multiverse? For example, if there are infinite universes, does this mean that in one universe you are a billionaire, while in another you never existed at all? Does the existence of a multiverse challenge our notions of free will, determinism, and the nature of reality? These are questions that philosophers and scientists continue to grapple with as they explore the implications of the multiverse theory. But the multiverse theory is not without its critics. One of the most significant challenges to the idea of the multiverse is that it is inherently untestable. Science is based on the principle that theories must be testable and falsifiable. That is, there must be a way to gather evidence that could prove a theory wrong. But the idea of a multiverse, especially in its most extreme forms, seems to violate this principle. If other universes are completely disconnected from our own, we have no way of detecting them, and there's no way to test whether they exist. This has led some physicists to dismiss the multiverse theory as speculative and unscientific. However, others argue that while the multiverse theory may not be directly testable in the traditional sense, it could still provide valuable insights into the nature of reality. For example, the theory could help explain certain aspects of the universe that are currently unexplained, such as the fine-tuning of the constants of nature. Many scientists have wondered why the laws of physics are so perfectly tuned to support life. If the strength of gravity were even slightly different, for example, life as we know it would not exist. The multiverse theory could offer a solution. If there are an infinite number of universes with different physical constants, then it's not surprising that at least one universe, like ours, happens to have the right conditions for life. In this view, the apparent fine-tuning of the universe is not a remarkable accident, but the result of a much larger and more diverse set of possibilities. String theory, which is one of the most promising frameworks for understanding the fundamental forces of nature, also supports the idea of a multiverse. According to string theory, the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings of energy. These strings can exist in multiple dimensions, and the way they vibrate determines the types of particles and forces that exist in the universe. However, string theory also predicts the existence of many different vacuum states, each corresponding to a different set of physical laws. In some models of string theory, the universe could be one of many that arise from different vacuum states, each with its own distinct laws of physics. This means that the multiverse is not just a speculative idea, but a natural consequence of the mathematics of string theory. There are also other versions of the multiverse theory that don't rely on inflationary cosmology or string theory. For example, the many worlds interpretation of quantum mechanics suggests that every time a quantum event occurs, the universe splits into multiple branches, each representing a different outcome of that event. In this interpretation, every possible outcome of every quantum measurement happens in some universe, creating a vast multiverse of parallel realities. While the many worlds interpretation is still controversial and not universally accepted, it provides a fascinating view of the nature of quantum mechanics and the possibility of infinite parallel universes. In addition to these theories, the multiverse also raises questions about the role of human consciousness and observation in shaping reality. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that reality does not exist in a definite state until it is observed. This leads to the idea that consciousness itself might play a role in determining the structure of the universe. If the multiverse is real, Could it be that our consciousness is influencing the creation of new parallel universes each time we make a choice? This idea brings us to a deeper, more philosophical view of the multiverse, one where human beings are not just passive observers, but active participants in the creation of reality. The search for evidence of the multiverse is ongoing, though it remains a challenging endeavor. One of the most promising avenues of exploration is the study of cosmic inflation. If the inflationary period of the universe occurred as theorized, it could have left behind detectable imprints in the cosmic microwave background radiation, the afterglow of the Big Bang. These imprints, if they exist, could provide evidence of other universes that were born from the same inflationary process. However, detecting these imprints is a highly complex task, and it may be years before we have the technology to do so. Despite the challenges, the multiverse theory has already had a profound impact on our understanding of the universe. It forces us to think beyond the confines of our observable universe and imagine a reality that is far larger and more diverse than we could have ever imagined. The concept of infinite universes, each with its own set of laws, opens up new possibilities for understanding the nature of existence and our place within it. Whether or not the multiverse exists, the very idea of it pushes the boundaries of human knowledge and forces us to confront the mysteries of the cosmos in new and exciting ways. As we continue to explore the universe and develop new theories and technologies, the multiverse remains one of the most profound and exciting areas of research. Whether we eventually prove its existence or not, the multiverse offers us a glimpse into the infinite possibilities of the cosmos and reminds us that the universe is far stranger and more complex than we can ever truly comprehend. The question of whether we are alone in the universe is perhaps the most profound and enduring of all scientific inquiries. For centuries, humankind has gazed up at the stars, wondering if life exists beyond our own planet. In ancient times, the idea of life on other worlds was relegated to myth and speculation. Today, however, it has become a legitimate scientific pursuit, with billions of dollars invested in missions to explore other planets, search for signs of extraterrestrial life, and even listen for messages from alien civilizations. As we continue to probe the vast expanse of the universe, one question remains at the heart of the search for extraterrestrial life. Are we truly alone, or is the universe teeming with life waiting to be discovered? The scientific search for extraterrestrial life began in earnest in the mid-20th century with the advent of radio astronomy. In 1959, two astronomers, Giuseppe Cocconi and Philip Morrison, proposed the idea of using radio waves to detect signals from extraterrestrial civilizations. They suggested that if an alien civilization existed, it might be transmitting signals in the microwave region of the electromagnetic spectrum, a part of the spectrum that is not absorbed by Earth's atmosphere. This idea sparked the creation of the Search for Extraterrestrial Intelligence, SETI, an ongoing scientific effort to listen for alien radio signals. SETI's early efforts focused on scanning the sky for narrowband radio signals, which would be distinct from the random noise in the universe. In 1977, one of SETI's most famous discoveries occurred. A strong, unexplained signal was detected from the constellation Sagittarius, lasting 72 seconds, but never repeated. Dubbed the "wow signal" after the astronomer who discovered it, the signal was never heard again, and its source remains a mystery. The wow signal is one of the most tantalizing pieces of evidence for extraterrestrial intelligence, but to this day, no one knows whether it was the result of an alien transmission, human error, or some natural cosmic phenomenon. Despite the lack of definitive evidence for extraterrestrial signals, the search for alien life has continued, evolving with the advances in technology and the discovery of new exoplanets. The last few decades have seen an explosion of interest in the search for life beyond Earth, driven by the discovery of thousands of exoplanets, planets that orbit stars outside our solar system. Many of these exoplanets are located in their star's habitable zone, the region around a star where conditions may be right for liquid water to exist. Water is considered one of the key ingredients for life as we know it, and the discovery of exoplanets in the habitable zone has sparked new excitement in the search for extraterrestrial life. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of exoplanets. Kepler's mission was to observe a small patch of the sky and monitor the brightness of stars for the faint dips in light caused by planets passing in front of them. This technique, known as the transit method, has been responsible for the discovery of over 2,600 exoplanets. Many of these planets are similar in size and temperature to Earth, and some are located in the habitable zone of their star, making them prime candidates for the search for life. In addition to Kepler, the discovery of the first exoplanet in 1992 and the detection of the first Earth-like exoplanet, Kepler 452b, in 2015, has significantly advanced our understanding of potentially habitable planets. These planets are located at distances that would allow for the existence of liquid water on their surfaces, and they may have conditions suitable for life. The hunt for Earth-like planets continues with missions like TESS, Transiting Exoplanet Survey Satellite, which is currently surveying a larger area of the sky in search of even more potential habitable exoplanets. While the search for planets in the habitable zone has garnered much attention, scientists are also exploring the possibility of life in more extreme environments. On Earth, life exists in some of the most inhospitable places imaginable, from the boiling hot springs of Yellowstone to the deep crushing pressure of the ocean's depths. If life can survive in such extreme conditions here on Earth, it stands to reason that life might also exist in similarly extreme environments on other planets or moons. This has led scientists to explore the possibility of life in the subsurface oceans of moons like Europa, Enceladus, and Titan. Europa, one of Jupiter's moons, is one of the most promising candidates for the search for life beyond Earth. Beneath its icy shell, Europa is believed to have a vast ocean of liquid water, kept warm by tidal forces from Jupiter's gravity. This ocean could potentially harbor life, protected from the harsh radiation of space by the thick ice above. In 2022, NASA's Europa Clipper mission was approved, which will launch a spacecraft to explore Europa's surface and subsurface in search of signs of life. Europa's potential for supporting life has captured the imagination of scientists, who see it as one of the best places to search for microbial life in our solar system. Similarly, Enceladus, one of Saturn's moons, has been the subject of much interest. In 2005, NASA's Cassini spacecraft discovered plumes of water vapor erupting from cracks in Enceladus's icy surface, suggesting the presence of a subsurface ocean. These plumes contain organic molecules, which are the building blocks of life, and they are ejected into space, making it possible to study the moon's potential for life without landing on it. In 2018, a study found that Enceladus's subsurface ocean could have the right conditions to support microbial life, further solidifying its status as a prime target in the search for extraterrestrial life. Titan, Saturn's largest moon, is another intriguing world in the search for life. Unlike other moons in the solar system, Titan has a thick atmosphere made up of nitrogen, methane, and other gases. Titan's surface is covered with lakes and rivers of liquid methane and ethane, and scientists speculate that, although vastly different from Earth's oceans, these methane seas could support life based on alternative biochemistry. The Huygens probe, which landed on Titan in 2005, provided some of the first direct measurements of this alien world. While life as we know it may not be possible on Titan, it is possible that some form of life, adapted to Titan's unique environment, might exist. The search for life beyond Earth is not limited to the planets and moons of our own solar system. As we look further out into the cosmos, the discovery of exoplanets in the habitable zone of distant stars has expanded the scope of our search. The Kepler and TESS missions have discovered many Earth-sized planets orbiting stars that are similar to our Sun, and some of these planets may have conditions that could support life. But even farther out, scientists are looking for signals from extraterrestrial civilizations. The search for extraterrestrial intelligence, or SETI, has been a topic of scientific inquiry for decades, though no definitive signals have been detected. One of the most famous efforts in the search for extraterrestrial intelligence was the WOW signal detected in 1977. This strong, unexplained signal was picked up by the Big Ear radio telescope, and it was never heard again, leading to much speculation about its origin. Some believed that it might have been a signal from an alien civilization, while others thought it might have been caused by a natural phenomenon. Despite years of searching, SETI has not found any conclusive evidence of extraterrestrial intelligence, but the search continues, driven by the hope that, one day, we will receive a signal from another civilization. The question of whether extraterrestrial life exists raises not only scientific questions, but philosophical and existential ones. What would the discovery of extraterrestrial life mean for our understanding of our place in the universe? Would it change our views on religion, philosophy, and the uniqueness of humanity? The discovery of even microbial life on another planet would have profound implications, suggesting that life is not a rare accident, but something that may be common throughout the universe. On the other hand, if we find no evidence of life beyond Earth, it might make us reconsider our own significance in the vast cosmos. The discovery of extraterrestrial life is, in many ways, the ultimate scientific quest. It challenges us to think about the nature of life itself, to question our place in the universe, and to ponder the mysteries of existence. As technology continues to advance and our exploration of the cosmos deepens, the possibility that we are not alone in the universe becomes more and more tantalizing. Whether we find microbial life in the subsurface oceans of Europa or Enceladus, or receive a signal from an alien civilization, the search for extraterrestrial life is one of the most profound and exciting pursuits in science. As we continue to explore the universe, we may not only uncover new forms of life, but also gain deeper insights into the origins of life on Earth and the conditions that make life possible. The question of whether we are alone in the universe may one day have an answer, but for now, the search continues. Whether we find life or not, the pursuit of this knowledge will push the boundaries of human understanding and expand our view of the cosmos in ways we can't yet imagine. As we explore the vast and awe-inspiring universe, we are constantly reminded of a humbling truth. Despite all of our advancements in science, technology, and philosophy, the limits of human knowledge are far greater than we often realize. Our understanding of the cosmos, though remarkable, is still in its infancy. With each discovery, we uncover new layers of complexity and mystery, revealing just how much we still have to learn. The more we know, the more we become acutely aware of the vast expanse of the unknown. The quest for knowledge has been an integral part of human existence for millennia. From ancient civilizations gazing up at the stars to the modern scientists who peer into the depths of the cosmos with sophisticated telescopes and spacecraft, humanity has always sought to understand the universe and its origins. Yet, for all our curiosity and drive, we still grapple with fundamental questions that have no definitive answers. How did the universe begin? What is the true nature of time and space? Are we alone in the cosmos? These are questions that continue to elude us, despite our best efforts to understand them. The concept of knowing itself is complex. For much of human history, knowledge was passed down through oral traditions and written texts, with great thinkers and philosophers contributing to our understanding of the world. However, with the advent of modern science, our view of knowledge has evolved. The scientific method, the process of observing, hypothesizing, testing, and refining, has allowed us to build an ever-expanding body of knowledge about the natural world. Yet, even with this rigorous approach, we find ourselves confronted with paradoxes and phenomena that challenge the very foundations of what we think we know. One of the most profound limitations of human knowledge lies in the sheer scale of the universe. The observable universe, as vast as it is only a small fraction of the total cosmos. Beyond the limits of what we can observe with our most powerful telescopes, there may be regions of space that are completely inaccessible to us. These distant realms are beyond the reach of any instruments we currently possess, and they may harbor secrets that we may never be able to uncover. The universe is simply too vast for us to fully comprehend, and our understanding is limited by the constraints of space and time. Even within the observable universe, our knowledge is incomplete. The universe is made up of billions of galaxies, each containing billions of stars, and around many of those stars we find planets and moons. While we have made incredible strides in studying these objects, there is still so much we do not know. For example, while we have cataloged thousands of exoplanets, planets that orbit stars outside of our solar system, we have barely scratched the surface of understanding what conditions might be required for life to exist on these distant worlds. The discovery of Earth-like planets in the habitable zone of other stars has sparked new hope that we might one day find signs of extraterrestrial life, but we still do not know the fundamental requirements for life to thrive in the universe. Perhaps one of the most elusive concepts in modern science is the nature of dark matter and dark energy, which together make up over 95% of the total mass and energy content of the universe. Dark matter, though it has been inferred from its gravitational effects on visible matter, remains invisible and undetectable by any current technology. Dark energy, which is responsible for the accelerated expansion of the universe, is similarly mysterious, with no known explanation for its existence or behavior. We can observe the effects of dark matter and dark energy, but their true nature remains a profound mystery, one that challenges our current models of physics and cosmology. In many ways, the search for dark matter and dark energy is a reflection of the limits of human knowledge. We know they exist, but we don't yet know what they are or how they fit into our understanding of the universe. The limitations of human knowledge also extend to our understanding of the fundamental forces that govern the cosmos. For centuries, the four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were thought to be separate and distinct. But in the 20th century, the theory of quantum mechanics began to suggest that these forces might be connected in ways that we cannot yet fully understand. For example, the theory of quantum electrodynamics, QED, has successfully unified electromagnetism and the weak nuclear force into a single framework, but gravity remains separate and distinct. The search for a unified theory of everything, one that can seamlessly combine all four forces into a single, elegant framework, is one of the biggest challenges in modern physics. But despite decades of research, we have yet to achieve this goal. One of the most profound questions in science is the nature of consciousness. While we have made great strides in understanding the brain and its functions, we still do not fully understand how consciousness arises from the complex interactions of neurons and synapses. What is consciousness, and how does it emerge from the physical processes of the brain? Is consciousness a fundamental property of the universe, or is it an emergent phenomenon that arises only in complex systems? These are questions that have puzzled philosophers and scientists alike for centuries, and they remain some of the most important unsolved mysteries in science. Some theories propose that consciousness is an illusion, a byproduct of the brain's activity, while others suggest that it is a fundamental aspect of reality, on par with space, time, and matter. We do not yet have an answer, but the search for the nature of consciousness continues to push the boundaries of neuroscience and philosophy. In the realm of cosmology, one of the most fundamental questions is the origin of the universe itself. The Big Bang theory, which suggests that the universe began as a singularity, a point of infinite density and temperature, is the most widely accepted explanation for the origins of the universe. But what happened before the Big Bang? What caused the Big Bang to happen in the first place? These questions remain unanswered, and the very nature of the Big Bang itself is still a subject of intense study and debate. Some scientists speculate that the Big Bang was the beginning of time and space, while others propose that it was simply a phase in an eternal cycle of expansion and contraction. Whatever the answer, the origin of the universe is one of the greatest mysteries in science, and it challenges our understanding of time, space, and causality. The limitations of human knowledge are not just confined to the physical universe. In the realm of philosophy, the question of what is reality has been pondered by thinkers for millennia. Are we living in a simulation? Is the universe real, or is it an illusion? These questions, while often dismissed as philosophical musings, have profound implications for our understanding of the world around us. Modern theories in quantum mechanics, such as the many worlds interpretation and the holographic principle, suggest that reality might be far more complex and strange than we can comprehend. The question of what constitutes reality and how we can know anything with certainty is one that has no easy answers, and it challenges the very nature of human perception and understanding. As we look to the future of scientific discovery, it is clear that there are still vast areas of the universe that remain beyond our grasp. The limits of human knowledge are not obstacles to progress, rather, they are invitations to explore, to push the boundaries of what we know, and to constantly ask the big questions. In some ways, the very fact that we don't have all the answers is what drives us forward in our quest for knowledge. It is the mystery of the universe, its vastness, its complexity, and its unknowability that continues to fuel our curiosity and drive us to explore the unknown. The search for knowledge is an ongoing journey, one that will never truly end. With each new discovery, we gain a deeper understanding of the cosmos and our place within it. Yet, with every answer we find, new questions arise, reminding us that the universe is far more mysterious and complex than we ever imagined. As we continue to explore the cosmos, we may never have all the answers, but the pursuit of knowledge itself will continue to be one of the most profound and important endeavors in human history. The limitations of human knowledge do not diminish the significance of what we have achieved. In many ways, the limits are what make our understanding of the universe so remarkable. The universe is vast, and there is still so much left to explore. But it is through our curiosity, our relentless pursuit of answers, and our willingness to embrace the unknown that we continue to expand the boundaries of human knowledge. In the end, it is not the answers we find that matter most, but the questions we continue to ask and the journey of discovery that lies ahead. Quantum mechanics, often called the science of the very small, is one of the most revolutionary and perplexing theories in the history of science. It deals with the behavior of particles at the most fundamental levels, the scale of atoms, subatomic particles, and even smaller entities. While the classical laws of physics, like those of Newtonian mechanics, offer an intuitive way to understand the behavior of everyday objects, quantum mechanics describes a reality that is radically different from what we experience in our day-to-day lives. It is a realm where particles can exist in multiple states at once, where objects can be entangled over vast distances, and where the very act of measurement can alter the outcome of an event. One of the most striking features of quantum mechanics is the concept of wave-particle duality. According to this principle, particles such as electrons and photons, particles of light, can exhibit both wave-like and particle-like behavior, depending on how they are observed. This was first demonstrated in the famous double-slit experiment, which is often cited as one of the most perplexing and counterintuitive experiments in physics. In the double-slit experiment, a beam of particles, like electrons or photons, is directed at a barrier with two slits. On the other side of the barrier, a screen detects the particles that pass through the slits. When only one slit is open, the particles behave like discrete objects, creating a pattern on the screen that corresponds to their particle-like nature. However, when both slits are open, something truly strange happens. The particles create an interference pattern similar to what you would expect from waves. This suggests that the particles are behaving like waves, spreading out and interfering with each other, even though they are individual particles. Even more baffling is the fact that when scientists measure which slit the particle passes through, the interference pattern disappears and the particle behaves like a classical particle again. This phenomenon suggests that the mere act of observation changes the behavior of the particle, a concept that challenges our traditional understanding of reality. The idea that the act of measurement collapses a particle's wave function into a definite state is known as the observer effect and is one of the central mysteries of quantum mechanics. At the heart of quantum mechanics lies the idea of superposition. This principle states that particles can exist in multiple states simultaneously, and only when measured does the system collapse into a single state. The classic example of this is Schrödinger's cat thought experiment. In this hypothetical scenario, a cat is placed inside a box with a radioactive atom and a vial of poison. If the atom decays, the poison is released and the cat dies. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, until the box is opened and the cat is observed, the cat is in a superposition of both alive and dead states. This paradoxical situation illustrates the strange and non-intuitive nature of quantum mechanics, where particles, or in this case, the cat, can exist in multiple states at once. Another concept in quantum mechanics that seems to defy logic is quantum entanglement. This phenomenon occurs when two or more particles become linked in such a way that their properties are correlated, regardless of the distance between them. When one particle is measured, the state of the other particle is immediately determined, even if it is light years away. This spooky action at a distance, as Einstein called it, appears to violate the principle of locality, which states that objects can only be influenced by their immediate surroundings. Entanglement has been experimentally confirmed in numerous experiments, and it has profound implications for our understanding of space and time. It suggests that the fundamental nature of reality is deeply interconnected, and that particles are not isolated objects, but are part of a larger, more complex system. This interconnectedness challenges our classical understanding of the universe, in which objects are assumed to be separate and distinct. In the quantum world, the boundaries between objects become blurred, and the connections between them transcend space and time. Quantum mechanics has also led to the development of quantum field theory, QFT, which is the current framework for understanding particle physics. QFT describes particles as excitations in underlying quantum fields, which are spread out across space and time. These fields interact with each other, and the interactions give rise to the fundamental forces of nature, such as electromagnetism and the strong and weak nuclear forces. In this view, particles are not individual objects, but are manifestations of the underlying fields, which are constantly fluctuating and interacting with each other. One of the most important and influential discoveries in the field of quantum mechanics is the Higgs boson, often referred to as the God particle. In 2012, scientists at CERN announced the discovery of the Higgs boson, a particle associated with the Higgs field, which gives other particles mass. The Higgs boson is a fundamental particle in the standard model of particle physics, and its discovery was a major milestone in our understanding of the universe. The Higgs field is thought to permeate all of space, and as particles interact with it, they acquire mass. This discovery not only confirmed the existence of the Higgs field, but also provided further evidence for the validity of quantum field theory. Despite the many successes of quantum mechanics, there are still many unanswered questions. One of the biggest mysteries is the relationship between quantum mechanics and general relativity. While quantum mechanics successfully describes the behavior of particles at the smallest scales, general relativity is the theory that describes the gravitational forces at large scales, such as those that govern planets, stars, and galaxies. These two theories, however, are incompatible in their current forms. Quantum mechanics describes space and time as being quantized, divided into discrete units, while general relativity treats space and time as a smooth, continuous fabric. The search for a unified theory of quantum gravity, which can reconcile these two theories, is one of the most important challenges in theoretical physics. One possible candidate for a unified theory is string theory, which suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. According to string theory, these strings can exist in multiple dimensions, with the way they vibrate determining the types of particles and forces that exist. String theory has the potential to unify the fundamental forces of nature into a single framework, but it is still a highly speculative theory and has yet to be experimentally verified. Another candidate for unifying quantum mechanics and general relativity is loop quantum gravity, which posits that spacetime is made up of discrete quantized units. In this view, spacetime is not smooth and continuous, but is composed of tiny loops or atoms of space. Loop quantum gravity seeks to merge the principles of quantum mechanics with general relativity, but it is still in the early stages of development, and has yet to provide a complete, unified theory. The strange and paradoxical nature of quantum mechanics has led to the development of various interpretations of the theory, each attempting to explain the meaning of its bizarre phenomena. One of the most well-known interpretations is the Copenhagen interpretation, which posits that particles exist in a superposition of states until they are measured, at which point the superposition collapses into a definite state. Another interpretation, known as the many worlds interpretation, suggests that all possible outcomes of a quantum event actually occur, but in separate parallel universes. While there is no consensus on which interpretation is correct, each offers a unique perspective on the nature of reality and the role of the observer. Quantum mechanics has had profound implications, not only for our understanding of the universe, but also for technology. The principles of quantum mechanics are already being used in the development of technologies such as quantum computers, which harness the strange properties of quantum particles to perform calculations that would be impossible with classical computers. Quantum computers have the potential to revolutionize fields such as cryptography, artificial intelligence, and materials science. The development of quantum technologies is still in its early stages, but it is clear that quantum mechanics will play an increasingly important role in shaping the future of science and technology. The strange world of quantum mechanics continues to challenge our intuition and expand our understanding of reality. The quantum realm is not just a collection of bizarre phenomena. It is the foundation of the universe itself. It governs the behavior of particles, the interactions of forces, and the fundamental structure of space and time. As we continue to explore the quantum world, we may uncover even deeper truths about the nature of existence, the fabric of space-time, and the limits of human knowledge. Quantum mechanics may not just be a theory about particles and waves. It may be the key to unlocking some of the greatest mysteries of the cosmos. As we look to the future of cosmic discovery, it's difficult to imagine how much more we could possibly uncover. Yet, with every breakthrough, we realize that the universe remains more mysterious and complex than we could have ever imagined. The next frontiers in cosmology, space exploration, and our understanding of the universe promise to be just as awe-inspiring as those that have come before. From cutting-edge technologies to new theories and innovative missions, the future of cosmic discovery holds the potential to answer some of the most profound questions about our existence, the nature of the cosmos, and even the fate of the universe itself. One of the most exciting developments in the future of cosmic discovery is the continued exploration of our own solar system. For decades, space agencies around the world have been sending missions to explore the planets, moons, and other objects within our cosmic neighborhood. In recent years, our understanding of the solar system has expanded dramatically, revealing that many of the planets and moons in our solar system are far more complex and intriguing than we ever thought. Yet, despite our progress, there is still so much we don't know about the worlds beyond Earth. Mars has long been a target for exploration, and the question of whether life ever existed on the red planet remains one of the most tantalizing scientific puzzles. NASA's Perseverance rover, which landed on Mars in February 2021, is tasked with searching for signs of ancient life, collecting soil and rock samples, and studying the planet's geology and atmosphere. In addition to Perseverance, NASA's Ingenuity helicopter, which made the first powered flight on another planet, is testing new technologies that could one day be used to explore the Martian surface more effectively. These missions, along with future ones, will help us answer the question of whether life ever existed on Mars and what the planet's history can teach us about the evolution of worlds in our solar system. Beyond Mars, the moons of Jupiter and Saturn have become the focus of increasing scientific interest. Europa, one of Jupiter's moons, is believed to have a subsurface ocean beneath its icy surface, and this ocean may harbor the conditions necessary for life. NASA's Europa Clipper mission, scheduled to launch in the 2020s, will study Europa in unprecedented detail, investigating its ice shell, subsurface ocean, and potential for life. Similarly, Saturn's moon Enceladus has been found to have plumes of water vapor spewing from its surface, indicating the presence of a subsurface ocean that could also harbor life. The upcoming Enceladus LifeFinder mission could provide further insight into the moon's potential as a habitat for microbial life. Titan, Saturn's largest moon, is another fascinating target for exploration. Unlike most other moons in the solar system, Titan has a thick, nitrogen-rich atmosphere and is home to lakes and rivers of liquid methane and ethane. While Titan's environment is vastly different from Earth's, some scientists believe that its unique chemistry could support forms of life that are radically different from those we are familiar with. NASA's Dragonfly mission, set to launch in the 2020s, will send a rotorcraft to Titan to explore its surface and study its organic chemistry. The search for life on these distant moons is not just about finding familiar life forms. It's about expanding our definition of what life could be and where it could exist. While the exploration of our own solar system is vital to understanding the potential for life beyond Earth, it is the search for exoplanets that will likely have the greatest impact on our understanding of life in the cosmos. Exoplanets, planets that orbit stars outside our solar system, have been the focus of intense study over the past few decades. The discovery of thousands of exoplanets has transformed our understanding of the universe and has opened up new possibilities for the existence of life beyond Earth. The question of whether we are alone in the universe hinges on the discovery of planets that are capable of supporting life. 1. Of the most significant missions in the search for habitable exoplanets is the James Webb Space Telescope, JWST, scheduled to launch in the coming years. The JWST is a joint project between NASA, the European Space Agency, and the Canadian Space Agency, and it promises to revolutionize our understanding of the universe. Unlike its predecessor, the Hubble Space Telescope, which observes in the visible and ultraviolet parts of the spectrum, JWST will primarily observe in the infrared. This will allow scientists to study the atmospheres of exoplanets in unprecedented detail, searching for signs of habitability, such as the presence of water, oxygen, and methane. JWST will also be able to observe distant galaxies, stars, and planets in their earliest stages, shedding light on the formation of the universe. Its ability to peer into the depths of space and time will allow astronomers to study the first galaxies that formed after the Big Bang, giving us a glimpse into the early history of the cosmos. The discovery of Earth-like exoplanets with the potential for life could have profound implications for our understanding of life's origins and the prevalence of life in the universe. In addition to JWST, other missions and observatories are also being developed to explore the universe in new and innovative ways. The European Space Agency's Plato mission, scheduled for launch in the mid-2020s, will search for Earth-like exoplanets by studying the stars in our galaxy. By measuring the tiny dips in light caused by planets passing in front of their stars, Plato will identify planets that are similar in size and temperature to Earth and are located in the habitable zone of their stars. The future of cosmic discovery is also intertwined with the search for extraterrestrial intelligence, SETI. Although we have not yet discovered definitive evidence of extraterrestrial civilizations, the search continues. Advances in technology, such as the development of more powerful radio telescopes and improved data analysis techniques, are making it possible to search for extraterrestrial signals more effectively. The next generation of radio telescopes, such as the Square Kilometre Array, SKA, will allow us to scan larger portions of the sky and detect faint signals that might have been missed by previous generations of telescopes. While the search for signals from extraterrestrial civilizations is still in its early stages, the discovery of even a single signal from an alien civilization would be one of the most profound moments in human history. It would change our understanding of our place in the universe, challenge our assumptions about life, and force us to rethink our views on technology, society, and our own future. As we explore the universe and study the potential for extraterrestrial life, we are confronted with the realization that the universe is far stranger, more complex, and more mysterious than we could have ever imagined. Whether we discover microbial life on Mars, find Earth-like exoplanets teeming with life, or receive a message from an alien civilization, each new discovery will bring us closer to answering the fundamental question: are we alone in the universe? The search for extraterrestrial life is not just about finding other forms of life. It is about understanding our own existence and the nature of life itself. As we continue to explore the cosmos, we may uncover new forms of life, new forms of matter, and new fundamental forces that will reshape our understanding of the universe. The future of cosmic discovery is limitless, and the possibilities for what we can learn are bound only by our imagination and our determination to explore the unknown. As we delve deeper into the mysteries of the universe, one question looms large: what is the fate of the universe? For centuries, the question of how the universe began was the primary focus of scientific inquiry. The Big Bang Theory gave us a starting point, a singularity, a point of infinite density and temperature from which the universe emerged and began expanding. But now, as we observe the accelerating expansion of the universe, another, perhaps even more profound question has emerged: how will the universe end? Will it continue to expand forever, leading to an increasingly cold and dark future? Or will it collapse back on itself, ending in a big crunch? Or perhaps the universe's ultimate fate lies in some other, as yet unimagined scenario? The fate of the universe is a subject of intense speculation among cosmologists, physicists, and philosophers. As we've discovered more about the expansion of the universe, dark matter, dark energy, and the large-scale structure of the cosmos, we've also uncovered a host of possibilities for how the universe might evolve and ultimately reach its end. The future of the universe depends on a variety of factors, including the properties of dark energy, the rate of cosmic expansion, and the laws of physics that govern space-time. While some of these factors are well understood, others remain shrouded in mystery. One of the most important discoveries in understanding the fate of the universe came in 1998, when astronomers discovered that the expansion of the universe is accelerating. This revelation, based on observations of distant supernovae, was completely unexpected. For decades, scientists had assumed that the gravitational pull of galaxies and other cosmic structures would eventually slow the expansion of the universe, leading to a big crunch, a collapse of the universe back into a singularity. Instead, the acceleration of the universe's expansion pointed to the existence of a mysterious force, which we now call dark energy. Dark energy is thought to make up around 68% of the total energy content of the universe, yet its true nature remains one of the biggest unsolved mysteries in modern physics. It appears to have a repulsive effect, counteracting the force of gravity and driving the accelerated expansion of the universe. If dark energy continues to dominate the evolution of the universe, it could have profound implications for its ultimate fate. One possibility is the Big Freeze, also known as the heat death of the universe. In this scenario, the universe's expansion continues indefinitely, causing galaxies to move farther and farther apart. As the universe expands, the energy that powers stars and galaxies dissipates and the universe cools down. Eventually, stars burn out and galaxies become increasingly isolated. The universe becomes a dark, cold, and empty place. Without stars, planets, or life, the universe would be left in a state of entropy, where no meaningful processes could occur. This scenario suggests that the universe, in the distant future, will become a frozen, lifeless void, with all matter spread thinly across an ever-expanding expanse. The Big Freeze could be the final end of the universe, but it would take an unimaginable amount of time, on the order of trillions of years. Stars will exhaust their fuel, and the remnants of collapsed stars, such as black holes and neutron stars, will eventually fade away, leaving behind a dark, cold universe. This long-term perspective on the universe's fate underscores the inherent transience of cosmic phenomena. Despite the vastness of space and the grand scale of cosmic time, everything we see today, from galaxies to stars to planets, is part of an ever-evolving process that will one day reach its conclusion. Another possible fate for the universe is the Big Crunch, which was originally proposed as a likely outcome of the universe's expansion. According to this scenario, the expansion of the universe will eventually slow down and reverse due to the gravitational pull of all the matter within it. As galaxies, stars, and other cosmic objects are drawn back together, the universe would contract, eventually collapsing into a singularity similar to the conditions that existed before the Big Bang. In this theory, the universe would effectively reset, undergoing a cycle of expansion and contraction. However, the discovery of dark energy has made the Big Crunch scenario seem less likely. The repulsive force of dark energy is pushing the universe apart, and as long as dark energy continues to dominate, the universe will continue to expand indefinitely, making the Big Crunch less probable. Yet, even though dark energy is pushing the universe apart, there are still other possible endings. Some theorists have proposed the idea of the Big Rip, a scenario in which the accelerated expansion of the universe becomes so extreme that it tears apart galaxies, stars, planets, and even atoms themselves. In this scenario, as the universe expands at an ever-increasing rate, the fabric of space-time becomes stretched to the point where it can no longer hold matter together. Ultimately, the universe would be ripped apart, with the very building blocks of reality being torn asunder. While this idea may sound like science fiction, it is based on a mathematical model of the universe's expansion. The fate of the Big Rip depends on the nature of dark energy and whether its influence continues to grow stronger over time. The Big Rip is a more dramatic and catastrophic end to the universe than the Big Freeze, but it is still a speculative scenario. The key factor in determining whether the Big Rip could occur is the equation of state of dark energy, a measure of how the density of dark energy changes over time. If dark energy's influence becomes stronger and stronger, it could lead to the accelerated expansion of the universe, reaching a point where it causes the Big Rip. However, this theory remains highly speculative, and the evidence for such a scenario is far from conclusive. While the Big Freeze, Big Crunch, and Big Rip represent some of the most widely discussed scenarios for the fate of the universe, there are also other, less conventional ideas. One intriguing possibility is that the universe could undergo a phase transition where its fundamental properties change in a way that alters its expansion and evolution. This idea arises from certain models of quantum gravity, which suggest that space-time itself may not be as fixed as we think. Instead, the universe could undergo radical transformations that lead to the emergence of new physical laws or even the creation of entirely new universes. This idea is speculative, but it points to the possibility that the end of our universe could be the beginning of something entirely new. The true fate of the universe may be determined by factors that we have yet to fully understand. The discovery of dark energy and its role in accelerating the expansion of the universe has dramatically altered our view of the cosmos, but dark energy itself remains one of the greatest mysteries in modern physics. We still don't know why dark energy exists, how it behaves, or what its ultimate impact will be on the universe. Some scientists speculate that dark energy could change over time, weakening or even disappearing, leading to a different outcome for the universe's fate. Others believe that dark energy is a fundamental part of the structure of the universe, and that its effects will only become more pronounced as the universe continues to expand. As we continue to explore the universe and develop new technologies, we will undoubtedly uncover more clues about its fate. Instruments like the James Webb Space Telescope, the upcoming Vera C. Rubin Observatory, and future space missions to study the cosmic microwave background will allow us to probe the universe in more detail than ever before. These observations could help us refine our models of the universe's expansion and give us a better understanding of the role that dark energy plays in shaping the cosmos. The future of cosmic discovery is filled with exciting possibilities. As we continue to push the boundaries of human knowledge, we may find answers to some of the most profound questions about the universe and its ultimate fate. The search for answers to these questions is not just about understanding the universe itself, it is also about understanding our place within it. The fate of the universe is tied to our understanding of time, space, and the fundamental forces that govern the cosmos. As we continue to explore the mysteries of the universe, we come closer to answering the ultimate question: what is the future of the universe, and what does it mean for us? The exploration of the universe is not just a scientific pursuit, it is a deeply philosophical one. As we look to the future, we are reminded that the universe is vast, and our place within it is fleeting. The ultimate fate of the universe is still uncertain, but the journey to uncover its secrets will continue to inspire and captivate humanity for generations to come. The universe's destiny is a reflection of our own, constantly evolving, expanding, and full of unknown possibilities.